This is our very last unit. We're going to be talking about correlation and regression, chi-square regression as well. This you are not getting a separate quiz on, but it will be on your final. So make sure that you watch these videos. There are going to be 4 videos in this folder. Okay, let's get started. So for most of the semester, we've been talking about one data set. On occasion, we would talk about a sampling distribution where we had multiple data sets and we took the mean of all of those data sets and then took the mean of the means. Here, we're doing a comparison between data sets. So we talked about this very briefly at the beginning of the semester, a correlation between 2 sets of data. The example that we used is during the summer, the number of ice cream cones that gets eaten increases, but so does the number of drownings. And we talked about, well, does that mean that eating ice cream will cause you to drown? So we talked about correlation versus causation, that sometimes we can see an increase in both sets of data, even though it's not necessarily related. In this case, we said that summer, the fact that it was summer linked the 2 sets of data. So in the summer, we buy more ice cream, and in the summer, we do a lot more swimming. So of course, if we're swimming, there are going to be more drownings. That's what correlation is. It can help you determine if there's some sort of relationship between 2 sets of data. So let's write that down. Sometimes there's a relationship, sometimes it's just a coincidence, sometimes there's some sort of third variable. So this is not a sure thing. Okay, this is the type of thing where it says, okay, well, it requires more exploration. If you remember in the previous unit, we were talking about hypothesis testing, and we said, well, you can support the claim, or maybe you don't have enough evidence to support the claim, or you can reject the claim, or maybe you don't have enough evidence to support the claim, depending upon whether the claim was the null hypothesis or the alternative hypothesis. If you don't have enough evidence to reject the claim, it means it warrants further investigation. That's what correlation is it's saying, okay, yes, there's a correlation. We need to investigate further as to why there might be a correlation. Or, no, there's no correlation. There's no relationship between these 2 sets of data. Okay, so for example, we might want to know, is there a correlation between the number of hours of sleep and the reaction time while driving? If you get less sleep, does your reaction time go down? Okay. Maybe the number of hours spent studying. Versus your grade on a test. Or one last example, the number of hours of training for an employee. versus the number of mistakes that that employee makes. Okay, these are things that people may want to investigate. If you're finding that your mistakes, that your employees are making a lot of mistakes, then you might want to determine, well, okay, should I be increasing the number of hours of training? And if you find that there's no relationship, right? The number of hours of training actually does not change the number of mistakes that an employee makes. Maybe if they receive 2 hours of training, some people make a lot of mistakes, some people make no mistakes at all, but that's true if they receive 20 hours of training as well. And then as a boss, what that's going to tell you is it's not the training that's causing the mistakes, it's something else that's causing the mistakes. So providing more training isn't going to do anything. Or if you see a relationship, you might say, okay, well, maybe I should be adding more training for my employees, and that might fix a lot of the problems that you're seeing. Okay. So what we're talking about is a relationship between two sets of data. And we've said in the past that the individual data points we can refer to almost like X values. Okay, now this is true. When we have two sets of data, we have one set of data where we refer to the individual data points as X values, and then the second set of data, we're going to refer to the individual data points as Y values. Okay, and each of these has a different role. So one variable is called the independent or explanatory variable, and the other variable would be the independent or the response variable. So what do we mean by that? Independent or explanatory variable is the one that you're changing, okay? That it's the one that you're not asking about. Okay, number of hours of sleep, this is sort of a given. The reaction time is the response variable. It's the one that's dependent on the other. Okay, we call it a dependent variable. So the reaction time while driving is what we think is dependent on the hours of sleep. It's easier, sometimes it can be easier to identify the dependent variable. Your grade on a test, we think, is dependent on the hours of time that you spend studying, okay? The number of mistakes that an employee makes, we think that that is dependent on the number of hours of training versus the other way around. Now, we can switch it, okay? We can always switch it, but we're going with what we think is dependent. Okay, so it's what it matters because the relationship that we're getting, okay, is going to change if we change which variable is dependent on the other. Okay, so if we look at students' grades on a test and then we look at, okay, well, does that change the amount of time that they spend studying? That's going to be a little bit different. So you want to think about, so for example, let's take the time studying and the grade on a test and think about the different ways that we could look at this. We could look at it as, does the number of hours that you spend studying affect your grade on a test? Okay, in that case, the number of hours spent studying is your explanatory or your independent variable, and your grade on a test is going to be your dependent or your response variable. So how does this change if we're changing which variable is which? The change in the question would be, do students with higher grades on tests get more sleep? Do they, where we might be asking, okay, I get A's all the time, I'm going to go to bed earlier so that I get higher grades. Okay, so then the number of hours spent studying would be your dependent variable or your response variable. Okay, so think about what question you're asking yourself. Okay, so A correlation requires two variables. One variable is the independent variable. We call this explanatory. And this would be our x variable. The other variable we call the dependent variable. Or response variable. And this is our y. Okay, so we could plot these, plot these x, y pairs and create something called a scatter plot. I'm going to put this in a different color because we're coming up with, this is about how we graph the relationship. This is another visual representation. So we spent a lot of time talking about visual representations at the beginning of the semester. This is an example of one. Okay, so for example, if we wanted to plot the data for number of hours of sleep versus reaction time while driving, then if we said you have 3 hours of sleep, the reaction time is 5 seconds, then we would be plotting the point 3, 5. And we're going to do an example of a scatter plot. Let's talk about what these scatter plots look like. And I will include these at the end of the board notes. But this is what I thought it would be helpful to have an actual graph here. Okay, so these are your different types of correlation. You have, so we're going to be talking about linear correlation, okay? And it both in this lecture and in the next lecture, only linear correlation. So we have two types of linear correlation. We have a negative linear correlation, which means that as we increase our x value, our y value actually goes down. So for the first example where we said the number of hours of sleep you get each night versus the reaction time while driving, we would expect that to have a negative linear correlation. As the number of hours increases, the reaction time is going to decrease, okay? We're going to be able to react more quickly. That would be a negative linear correlation. Then we have a positive linear correlation, which means that both variables are increasing. So that would be an example of number of hours you spend studying versus your grade on a test, right? The more hours you study, the higher your grade on the test. Then you have examples where maybe there is no correlation, okay? What might be an example of that? The number of hours, the number of glasses of milk that you drink affects your reaction time while driving, okay? I think that we could be pretty confident that it makes no difference, that sometimes people may drink 8 glasses of milk and their reaction time might be 40 seconds, whereas some people might drink 2 glasses of milk, their reaction time might be 10 seconds. There are some people who drink 2 glasses of milk and their reaction time might be 3 minutes. Okay, there is no correlation between those two, I'm assuming. Okay, Then there's a correlation, but maybe it's not linear. Maybe as it increases, as x increases, y will increase, but then it reaches a peak. And now as y increases, as x increases, y will start to decrease. Okay, so you might have something nonlinear. What would be an example of something nonlinear? If you throw something, okay, originally, as it gets further away from you, its distance from the ground increases. But at a certain point, it reaches a peak, and now, as it gets further away from you, its distance from the ground decreases. Okay, so we do have some examples of nonlinear correlation. In fact, most examples, most relationships between data, okay, are probably nonlinear. Okay, there are lots of other. We have exponential relationships. We have logarithmic relationships, for those of you familiar with logarithms. We have parabolic relationships, like this one looks parabolic. So we have all kinds of relationships. We're only going to be talking about linear relationships. Okay, so these are the different linear. We have negative, we have positive, or we have no correlation, or we have something that looks like a correlation. And we could estimate the type of correlation from the scatter plot. Okay, so how do we construct a scatter plot? Let's use an example. So I'm going to write out this example, but I wanted to say it to you first. Let me make this a little bit bigger. Okay, so suppose that we have a director of alumni affairs at a small college, and he wants to determine whether there's some sort of linear relationship between the number of years that alumni have been out of school and their annual contributions. Okay, so let's say that you graduate from BMCC, okay, not exactly a small college, but you graduate from BMCC. We want to know, if you've been out 1 year, are you giving any money back to the school? If you've been out 5 years, are you giving any money back? And if you are you giving more money back because you've been out of school longer? What if you've been out of school for 20 years? Okay, now why do we want to know this? We want to know who we might reach out to for money, okay, because obviously we're going to reach out to people who are more likely to give. Why would we feel that people who have been out of school longer are more likely to give? Well, they've been working longer. Maybe they started to pay off student loans, so they have more money in their pockets. Maybe they've been promoted at their job, so their salary is higher. So there are a lot of reasons for thinking that there might be a relationship, but that doesn't necessarily mean that there is, okay? It could just be that it has nothing to do with how long you've been out of school. It has to do with what salary you have when you get out of school, or it has to do with how many activities you were involved in when you were in the school. Maybe the more attached you were to the school, the more likely you were to give contributions, okay? So there might be a relationship. It seems like there would be a relationship, but we don't know for sure. And that's why we do these problems, because this will say, okay, yeah, reach out to the people who have graduated, 10, 20, 30 years ago, versus maybe instead of reaching out to those people, I should be looking at people who are involved in different extracurricular activities and see and reach out to those people, whether they graduated 1 year ago or 10 years ago. Those are the people to reach out to, okay? So let's do this problem. So first of all, I'm going to just put in, this would be a negative correlation, we said. I want you to see if you could graph these on your own. And when I say graph them on your own, I mean right now, pause the video and say, okay, what does a positive correlation look like? Positive linear correlation. I want to put this in here just so that you, when you look back at the board notes, you see what we discussed when, but I'll put in the other graph so that it's nice and clear. Okay, positive linear correlation. It looks almost like a line, right? But as x increases, y will also increase. No correlation is, it's just completely scattered. It's all over the place. It looks almost like a horizontal line. Okay, everything is just completely scattered. And this is one example of a nonlinear correlation. It is not the only example. So let's just create a scatterplot. And this is often constructed from sample data, right? We're not going to ask all of the alumni. We're not going to go to all of the alumni and see how much they have contributed. We're just going to go for a sample. We're going to take, maybe 20 alumni or 40 alumni. In this case, we only took 7 alumni to try and determine if there's a correlation. Okay, so suppose the director and we're going to be reusing this data throughout this lecture. Now again, if this were not linear, if it were quadratic, it would change who the director reaches out to, right? If it were quadratic and it's decreasing at some point when our number of years out of college gets very, very large, then we're not going to reach out to those people. So knowing what kind of correlation is important, okay? This is just, is it linear or not? And correlation is a relationship. And we'll say their annual contribution in thousands of dollars. Okay, so let's think about the independent versus the dependent variable. What does the director think is dependent on which, right? He thinks that the annual contribution is dependent on the number of years out of school. So annual contribution would be your Y, or your response variable. Think about it this way. If he's looking at who to reach out to, he's not looking at their annual contribution. He's looking at the number of years that they've been out of school, right? And if he were to look at this data and see, yes, there was a relationship, he's going to go through all of the records of the students and say, how long have they been out of school? Not what was their annual contribution, because that's not what's going to tell us who to reach out to. okay? The annual contribution is dependent on the number of years out of school. So the data that you're given, so this would be collected from a sample. This is your X. Remember, it matters. If you switch the X and the Y, it changes whether it's a negative correlation or a positive correlation. If there's no correlation, it won't matter. So we have 1 year out of school, 10, 5, 15, 3, 24, and 30. Now there's no repeats here. Now you're taking it from a sample. It's certainly possible that there would be repeats, okay? So I'm just going to put that in a different color. There don't happen to be any here, but it's possible that there would be. And you should be taking a random sample. So it's possible that you would take somebody who's been out of school 1 year and another person who's been out of school 1 year. And they might have different contributions, okay? That's why your graphs look like this, where they have all of these dots, right? And sometimes they're one right on top of each other, okay? It's just overall, if you look at the general shape, this is a line with, actually, if you think about the line it has, for those of you who are familiar with the equations of lines, it would have a negative slope, whereas this one would have a positive slope, okay? And we're going to talk about that in the next lecture. So how do we graph this? Well, we need the y's first. So this is 12.5. Again, this is given to you. If it's not given to you, then you would have to go out and collect the sample data yourself. Okay, so we're just going to draw a quick scatter plot here. So we have our X and our Y. Our X is going to go up to 30, so let's go up by 5s. Okay, our Y's go up to 14.6. Let's go up by 1s here, okay? Hopefully I left enough room. I think that's enough room. So this is 2, 4, 6, 8, 10, 12, 14. It should be okay. Okay, here's our X. So this is number of years out of school. This is contribution. And now we're just plotting our data points. We have 1, 12.5. So 1 is somewhere around here. 12.5 is about here. So 1, 12.5 would be our first point. Then we have 8.7, which is somewhere around here. 8.7, 10, 8.7. Then we have 5, 14.6. 15, 5.2. We're approximating here. 3. Back here, 9.9. 24, 3.1. And 32.7. Okay, so it looks kind of like this. Well, what does this look like? This kind of looks like a negative correlation, okay? It's not a lot of data points, so it's a little hard to see, but it looks like it's kind of negative, okay? So negative correlation. Okay, let's take a look at another one. Let's suppose a student conducts a study to determine if there's a linear correlation. And we'll say between the number of hours a student exercises per week and their GPA. Now this could be a good study, right? Exercising is good for you. It keeps you healthy. It releases endorphins in the brain. It might help you focus more. So it's certainly a reasonable study. It's not like this is crazy, okay? And what would happen if a student found that there was a relationship, a linear correlation? Maybe they're going to spend some more time exercising. Or maybe a student who thinks it's really helpful and has been exercising like crazy is going to say, this is not, I don't have to exercise so much. I can, it's good for my health and everything, but maybe I should like take a break every once in a while. So they'd take a sample. I think in this one, I don't have any repetitive X values either. But again, certainly you can, if you take a sample, you can have students who, multiple students who say that they exercise 3 hours per week. So it just depends on your sample. So the data that was collected, you have hours of exercise. This is your X values. And then you have GPA. So for hours of exercise, we have somebody who does 12, 3, 0, 6, 10, 2, 18, 14, 15, and 5. Okay. And their corresponding GPAs, 3.6, 4.0, 3.9, 2.5, 2.4, 2.2, 3.7, 3.0, 1.8, and 3.1. Okay, and our GPA is the Y. So the GPA is what we believe to be dependent on the hours of exercise. Okay, so let's plot it. So hours of exercise, we could go up by 2s, let's say. 2. We know that we go all the way to 18. Okay, here we're going to go up by 1. Let's go up by 0.5. And again, you don't have to mark off every thing that you see here. Probably could go up higher. 3.5. And 4, this is the GPA. Okay, and we're trying to determine, is there a correlation? Well, these are our different points. So this point is 12, 3.6, right? This point, for example, is 5, 3.1. That's how we're plotting it. These are our coordinates. So 12, 3.6 is about here. 3, 4 is about here. 0, 3.9, we're here. 6, 2.5. Then we have 10, 2.4. Then we have 2, 2.2. 18, 3.7. So our x is 18. Our y is 3.7. Our x is 14. Our y is 3. Our x is 15. Our y is 1.8. And finally, our x is 5. And our y is 3.1. And we could see here, there is no correlation here. Okay, this does not look like a line with a negative slope. It doesn't look like a line with a positive slope. It doesn't even look like it might be some other shape. This looks like no correlation. Okay. Okay. So the scatter plot could give us a pretty good idea. Here's the thing though. It can be a little subjective, right? I might say that this looks like no correlation, and you might say it looks a little positive, actually. So we have to take care of this problem, right? And the only way to take care of this problem is to have some sort of precise measurement. Because otherwise, you know, it was like with the outliers. Well, that seems like a really large number. Actually, I don't think it's that large a number. And you start to have disagreements. So we need to take care of that. So the precise measurement is a correlation coefficient. So looking at a scatter plot, to determine correlation can be subjective. It's not that it's not useful at all, right? Even if we said that, even if you looked at this and you said, well, it looks a little bit positive, we know that even if it's a little positive, it's not a strong relationship. It's a very, very weak relationship. Okay, so we look at the correlation coefficient. So the type would be positive or negative. We call it the correlation coefficient. Okay, so it gives us an actual number. Okay, R, so I'm doing this as handwritten, okay, but it's an R, it's usually italicized, okay. This represents, we call it the sample correlation coefficient. That's because it's the correlation coefficient based on the sample. Okay, it's based on the sample data. Now we have the we have the population correlation coefficient. And again, there's not really a good way for me to do this if I'm writing it by hand, but it looks like a P, okay? But it's actually pronounced, it's actually R-H-O, it's Greek letter, and it's pronounced rho. And this would be the population correlation coefficient. Okay, so we use the sample to predict the population, right? We use our correlation coefficient from the sample to say, okay, yeah, our correlation coefficient for the population is, there is a linear relationship, okay? Or there's not a linear relationship. So first of all, the range of R is -1 to 1. Where when R is close to 1, there is a strong positive linear correlation. And when R is close to -1, there is a strong negative correlation. Kind of makes sense. And when R is close to 0, there is no correlation. Think of this as the slope of a line. Okay, when your slope is +1, then it looks very linear. When your slope is -1, okay, it's a negative correlation. When your slope is 0, if we go back to here, okay, this looks like a slope of 1, -1. This is like 0. There's no line. There's nothing. Okay. Okay. How do we calculate it? So I'm going to give you the formula. One of the things that I suggest for your final is that you make a list of all of your different formulas and all of how you get all of your different standardized test statistics. This is a case where you want to write down your formula. Okay, so we have R is equal to N, which is the number of pairs that you have. So it's your sample size, okay? The sum of your X times your Y. So you take your X, you multiply it with your Y, and then you add all of that together, okay? So for every pair, you're taking your X times your Y, you take the sum. Remember, that's what this sigma means, okay? This is an uppercase sigma in Greek. The lowercase sigma is your standard deviation. Minus, then you take the sum of all of your X, and you multiply by the sum of your Y's. Then you're going to divide. And it's taking the square root. This is a beautiful formula of N. Then you take each of your X's and you square them, and then you take the sum of those. Then you take your sum of your X's and you square that number. So we're going to go through an example. And then it's N, and the same thing for your Y. You take every Y value, square it, and then you add all of that together. And then you take the sum of your Y values, and you square the sum. Okay, beautiful formula. I will tell you, almost all the time people use technology for this. They don't do it by hand because it is so complex, okay? But we're going to do an example by hand just so that you get accustomed to it, okay? And this is just the type of thing where you're just doing things very slowly. So we're going to do the example of years out of school. We're going to use the example from before. Okay, versus the annual contribution. So we had 1, 12.5. This is the same data from before. I'm giving it to you. 10, 8.7, 5, 14.6, 15, 5.2, 3, 9.9, 24, 3.1, and 32.7. And once again, over here, N is equal to sample size. Sample size is the number of pairs that you have. So here, if we count, we have 1, 2, 3, 4, 5, 6, 7 pairs. So n is equal to 7 here. Now we're just going to calculate each of these things individually and then plug in. So we need to calculate sum of x times y. So what is this? This is 1 times 12.5. That's the first x times y. We're going to add that to the 10 times 8.7 plus 5 times 14.6 plus 15 times 5.2 plus 3 times 9.9 plus 24 times 3.1 plus 30 times 2.7. What is this equal to? This is equal to 435.6. Okay, you could try it in your own calculators. Then we have to keep going. So what else do we have to calculate that I see here? I see that we have to know what the sum of x is. Okay, so the sum of our x's, and we'll have to know the sum of our y's. So we're going to calculate that. So the sum of our x just says add all of your x's together. That's equal to 88. Then we have the sum of our y's. So the sum of our y's, we're just adding all of the y's together. Sorry, this comes out on such a slant. So what is that equal to? That's equal to 56.7. Okay, then we have to do the sum of our x squares. So this means that we're taking each of our x values and we're squaring them and adding all of that together. So these are our x values. And if we do that, we get 1,836. Now we need to do the same thing for our y. So we're going to take each y value, square it. So 12.5 squared, 8.7 squared. We take each one and we square it. And then we add all of those numbers together. You can see that this is a lot of tedious work. So yeah, when you have, if you were to take another statistics class, you would do this on a calculator or you would do it in Excel. This gives you 587.05. So now that we put all of that, now that we calculated all of that, we could just plug in numbers. So I'm going to repeat what the formula is. The R is equal, the correlation coefficient is equal to N. So we do 7 times the sum of our x, y. So if you go back, the sum of our x, y was 435.6. So it's 7 times 435.6. And then the sum of x was 88. The sum of y was 56.7. So we're just plugging in these numbers and we're doing the same thing down at the bottom. Okay. So I'm just going to rewrite this because it got a little messy. So we're going to have 7 times 435.6 minus 88 times 56.7. And then that whole thing is divided by the square root of n, which is 7. Then the sum of the squares for x, so 1836, minus the sum of x squared, so minus 88 squared. And then times, same thing for the y's. 7 times the 587.05. And then minus whatever our sum for the y's were, which was 56.7 squared. Okay, and if you do a slow calculation for this, this will give you negative 1,797.6. That's what the top comes out to. And then the bottom comes out to the square root of 5108 times the square root of 894.46. And you get negative 0.841. So this is close to negative 1. Close to negative 1. It's a relatively strong negative correlation, which is what we found from the scatter plot. Right? It looked like a relatively strong negative correlation. Okay. Just to give you the math for the second one so that you can sort of practice. Okay. If we use the other data set where it was hours of exercise, I'm putting in an extra C here. I don't know why I'm doing that. I think I did that on the other one too. I don't know why I did that. I don't think there's a C. Okay, so we had hours exercise and then GPA. So our data was 12, 3.6, 3, 4.0. Then we had 0, 3.9. 6, 2.5, 10, 2.4, 2, 2.2, 18, 3.7, 14, 3.0, 15, 1.8, and 5, 3.1. And our n here is 10. There are 10 pairs. Okay, so we identify our n first. Then we're going to want all of those values. So we're going to do the sum of x, y first. So this is 12 times 3.6 plus 3 times 4 plus 0 times 3.9 plus 6 times 2.5 plus 10 times 2.4 plus 2 times 2.2 plus 18 times 3.7 plus 14 times 3 plus 15 times 1.8 plus 5 times 3.1. And what do we get there? We get 249.7. Then we need the sum of our x. So we take all of our x values and we add them. And what do we get? 85. Then we take the sum of the y. So we take all of our y values and add them. And we get 30.2 for that. Okay, then we have to do the sum of x squared. So you can see the difference. We take each x value and we square it. So we're doing 12 squared plus 3 squared plus 0 squared plus 6 squared plus 10 squared plus 2 squared plus 18 squared plus 14 squared plus 15 squared plus 5 squared. And if we do that, we get 1063. And then finally, we have the sum of y squared. And we get 3.6 squared plus 4 squared plus 3.9 squared plus 2.5 squared plus 2.4 squared plus 2.2 squared plus 3.7 squared plus 3 squared plus 1.8 squared plus 3.1 squared. And we get 96.56. So when we calculate r, on top we have n times the 249.7. So times this, because that's the sum of x. Sum of xy. And minus, and it was the sum of x, so 85, times the sum of y, so 30.2. And then that whole thing is the square root of 10, which was our n, times the sum of x squares, so 1063, and then minus the sum of x, and then take that number and square it. And then we do the same thing for the y's. So it's 10, except now it's times 96.56 minus the sum of our y's squared. Okay, if we break that up, we get negative 70 on top over the square root of 3,405 times the square root of 53.56. And this gives us negative 0.164. Okay, this is close to 0. So there's no correlation, which is what we found in the graph, in the scatter plot. Okay, so the only thing here is it's still kind of subjective, because now we have an actual number, but then what do we consider close enough to -1 to warrant a relatively strong negative correlation? So how can we figure this out? Okay, well, we can make a conclusion using a rejection region. Okay, so once we calculate r, we want to decide if this is significant, right? If the population correlation is significant. Okay, and we want to know with a certain level of significance. So we had a level of confidence. Now we have a level of significance. We use the same exact thing. Okay. So what does this mean? This is the percentage of times when we decide the correlation is significant when it's not. In other words, alpha is equal to 0.01. So 1% of the time we're wrong. We say there's a significant correlation, but there's not. Okay? So I'm going to put it in black because this is hard to see and I just forgot to change colors. So typically, alpha is equal to 0.01 or 0.05. These are the most typical values. It's not the only value, but it's the most typical value. Okay. So what are we saying? %, or 95% of the time. We correctly decide a correlation is significant. Okay, so we use the absolute value of R to do this. And we also use it's called the Pearson critical value chart. So this is what it looks like. Okay. So it's another chart. It's easy to use though. Okay. So we look at the N and then we look at the alpha. So for example, in the first one, our N was 7. So we look at 7, and if we want 5% significance, 5% significance, then our value would be 0.754. Okay, and what we're doing is we're saying if the absolute value of R is greater than the value in the table, the correlation is significant. Okay. Otherwise, it's not that it's not significant, it's that there's not enough evidence. Not enough evidence to say it's significant. Okay, so in data set 1, I'm going to indicate data set 1 is the one with years out of school so that I'm not constantly rewriting it. And in data set 2, that was the one with exercise, number of hours of exercise. So in data set 1, we calculated R to be negative 0.841. So let's see if it's significant based on the table, okay? Is it significant? Assuming alpha is equal to 0.01. Okay, well, how do we do this? So in our chart, we look at alpha equals 0.01 and n equals 7. So we go to our chart. Alpha, n equals 7, alpha equals 0.01. So we get 0.875. Okay, so now we're looking. Is absolute value of R is less, so first of all, absolute value of R is positive 0.841. Absolute value just says get rid of the negative signs, okay? So the thing is that the absolute value of R is less than 0.875. So therefore, there's not enough evidence to say it's significant. Now let's ask the same question, but this time, is it significant? Assuming alpha equals 0.05. So in our chart, we look at alpha equals 0.05 and n equals 7. And if we go to the chart, alpha equals 0.05, n equals 7, we get 0.754. And in this one, 0.841 is greater than 0.754. So we say the correlation, the relationship, is significant. Okay, let's just quickly, I'm not going to write this down because it's not necessary because we already know that there's no correlation. With the other set of data, okay, in data set 2, we calculated R to be negative 0.164. Now, and n was equal to 10. right? If we go to the table, you're going to see really clearly when n equals 10, we have 0.632 and we have 0.765. 0.164 is nowhere close to those. So there's not enough evidence to say that the relationship is significant, okay? Nowhere near enough evidence. So at 10, we don't even have to bother. Whereas at 7 with a 0.841, depending on how often we're comfortable being wrong, okay, whether it's 5% of the time or 1% of the time, and you could see why it's subjective. That negative 0.841 could suggest to some people it's a strong negative correlation, and to others that it's not as strong, okay? Okay, so we're sort of at the end, okay? So how can we use, what we're really doing here is we're using a hypothesis test, okay? To determine correlation significance. Okay, so we only consider a two-tailed test. Now, why is this? Because our alternative hypothesis and our null hypothesis are always the same, okay? H sub 0 is always going to be that our rho, okay, our P is equal to 0. No significant correlation. That's what the null hypothesis says. And the alternative hypothesis is always a non-equals. Our rho is not equal to 0. Which means that there is a significant correlation, right? Remember we said as R gets closer to 0 means that there is no correlation. So this is just the population correlation coefficient we're saying is the same thing. When it's at 0, there's no significant correlation. When it's not at 0, there's significant correlation. So this means if we reject the null hypothesis, there is a significant correlation. Okay, how do we do this? We use a t-distribution. So we're using a different table. We're using that t-table. Okay. The degrees of freedom that we use is n minus 2. So these hypothesis tests work in the same way, right? We have a rejection region, we have a test statistic, we have standardized test statistic. So the test statistic is your R. The standardized test statistic is your R over that standard deviation. And the way that we find that is square root of 1 minus R squared over n minus 2. Okay, and that square root goes over the whole thing. I'm going to write it clearly. It goes, this whole thing is under the square root. Okay. Okay, so we need to determine if we're in the rejection region. Okay. So we did a whole unit on hypothesis testing. So this should not be new. Okay. So example, we're going to use data set 1. Okay. So 1. Now usually we would determine if it's if it approximates the t-distribution or normal distribution. We're not going to do that because the way that we would do that is something that you haven't learned. Okay, so I'm going to leave that out of here. You're going to assume that it approximates. You're going to assume that everything is right. Okay, so identify your hypotheses. This is always the same. So your null hypothesis is that that rho is equal to 0, and your alternative hypothesis is rho is not equal to 0. Okay. 2, identify alpha and your degrees of freedom. So here, let's use alpha as 0.05. And our degrees of freedom is n minus 2. Well, n in that example was 7. So 7 minus 2 is equal to 5. Okay. Okay. 3. Find the rejection region using the t-chart, right? So let me open that. Just ignore what you're seeing. This is just how I organize all of your files. I didn't put it under there. Confidence intervals. Okay, so here's your t-distribution. So we're looking up 2 tails. We're only looking at the 2-tail test, okay? Alpha is 0.05, and your degrees of freedom is 5. So your t sub 0 is 2.571, okay? So alpha is 0.05. We're looking under 2 tails. Degrees of freedom is 5, 2.571. So t sub 0 is equal to 2.571. So our rejection region, it's 2-tailed, so it's either less than negative 2.571 or it's greater than positive 2.571. So now we calculate the standardized test statistic. Okay. Remember that our R was equal to negative 0.841. Okay. This we calculated already. So it's possible that on the test, it might give you an R. It might say, okay, we have a data set for which the correlation coefficient is negative 9.2, negative 0.92. Okay, so we already calculated this, so we don't have to calculate it again. And then the next thing would be is to make a decision. So negative 0.841 is less than, sorry, we never calculated I have to go back. We never calculated I gave you the R, but we didn't calculate the T. So T is equal to negative 0.841 over the square root of 1 minus negative 0.841 squared over 5 in this case. And we get negative 3.48. Okay, so now number 5, I'm going to put it here because I don't know if it'll fit. 5, make a decision. So negative 3.48 is less than negative 2.571. Okay, it is less than. So what's our decision? Our decision is that there is, so we reject the null hypothesis. So there is a significant correlation. Can you see this? You can. You can't really. We reject H sub 0. So there is a significant correlation. Okay. Let's do one more. Let's do example 2. So data set 2. Okay, and for this one, remember R was equal to negative 0.164. That's what we had previously calculated. Okay, and let's do alpha equal to 0.01. Okay, just so that you have something different. So first thing that we do is we identify the null hypothesis and the alternative hypothesis, always the same. Null hypothesis is that our correlation coefficient is equal to 0, right? Our rho. Alternative hypothesis, rho is not equal to 0. Here, our alpha is 0.01, and our degrees of freedom is 8, because we had 10 pairs. Then, our T sub 0. So we go into our T chart. So in our T chart, we're looking at 0.01 in the two-tail test. And then we go down to 8. It's 3.355. 3.355. I'm actually going to change this. Let's not do 0.01 because we know that there's no way it's 0.01. Let's do 0.20. Okay, let's make it really large. Just because we already know there's no way. So let's make this 0.20. And let's go back into our T chart and look up 0.20 for a two-tailed test. So we're going to this one, 2 tails, 0.20. We're going to 8. It's 1.397, much smaller. So let's see what happens. 1.397. So it's a two-tail test. So remember that means that our rejection region is either less than 1.397 or greater than positive 1.397, right? Less than the negative, greater than the positive. So now you have to calculate t. So t is equal to r over the square root of 1 minus r squared over n minus 2. So our r was negative 0.164 over the square root of 1 minus negative 0.164 squared over n minus 2, which was 8, right, over our degrees of freedom. And practice putting this into your calculator, but you get negative 0.47. So even here, in this instance, we're outside of the rejection region. So we fail to reject h sub 0. And when we fail to reject h sub 0, we're saying there's no significant correlation. So in the other case, we rejected. When we reject, we're saying that there's a significant correlation. Here we're failing to reject, so there is no significant correlation. Okay. And just one quick note before we end. Correlation does not imply a cause and effect relationship. So be careful about that. It could. It doesn't mean that it's not possible. It could also be that somehow y causes x. So maybe the number of hours that you sleep doesn't affect your reaction time. Your reaction time affects your number of hours that you sleep. Okay. Maybe it's that there's some sort of third variable. That's like the swimming and the number of drownings, like the number of drownings and the number of ice cream cones eaten, where the third variable is the time of year. And it could be something that we do or we don't know about. Or it could just be a coincidence. So there was a study that was done that said the more milk you drink, the more likely you are to get a divorce. Okay. I think that we could all agree that that is an example of a coincidence. I don't think how much milk you drink changes whether or not your marriage is going to last. So sometimes it's just a coincidence. Okay. So just things to keep in mind about your conclusions. Okay, and that's it. There was a lot of information here, but a lot of it is repeat, right? Essentially, you're looking at relationships. You can look at it graphically through a scatter plot. You can calculate this correlation coefficient that we have, which takes more time. Usually it's done using technology. And you can compare it to what you see in the critical value table for correlation coefficients, right? That's this table here. So you can look here. That could help you determine. Or you can do a hypothesis test using the t-distribution. Okay, that's essentially what we looked at. And the hypothesis test should be a complete repeat to you. Okay, that's it.